Okay, so let us continue with our slides about qualifiers and quantifiers. We're on to the quantifiers part now, of course, but we learned how to formally specify ideas. Like, I would like to formally specify that every non-empty list of numbers has a minimum, so that I could then go and prove that using some mathematical technique. I want to go in and specify that a list of numbers is sorted. And here is how I can specify that. And then I can go and prove that if I have an L, if this is true, it must be sorted. Things like that. So this is just a statement. This is just something in math that we can prove or disprove. Let me show you one way to prove it. One way to prove it is to actually write a program. Programs can be proofs, which is surprising. And so let's go full circle. Let's start with an English description of what we'd like to do. Let's translate that to a mathematical, formal, logical statement that has maybe quantifiers in it. And we'll go from that then finally to a piece of code that will be able to, beyond a shadow of a doubt, prove that your formal statement that you wrote that describes your problem is true or false. You can either prove or disprove it, and that's the idea. So that's where we're going, and I need to teach you a term. Do you remember the term proposition? First of all, that's something we talked about a long time ago. That is just something that is true or false, because I'm building on top of that. So a proposition is something that's true or false. Like if I go and I say it's raining today, that is a true proposition, and then you can go out and look and prove it. Okay, something that is true or false. I gave you an example way back when of something that could not be a proposition, like this sentence is false or something weird like that. True or false. But a proposition is something you can prove. Something that is either true or false, not both, not neither. Okay? So like it's raining today is a proposition that is actually true. Maybe tomorrow it would be false. Raining strawberry today. So that's just a proposition. It is a statement that you could say is either true or false, right? And you can just look out the window and tell. Or look at the forecast and tell. A predicate is a proposition. So a predicate is a special kind of thing that could be proven to be true or false. But the power of a predicate is that it has some variables inside of it. That's the goal, all right? And the reason I'm going here is because a lot of our quantified statements, with like a for all or there exists inside of them, they had variables that they needed to quantify over, we say. And so here's an example predicate. It's just a proposition with some variables in it. It's just like instead of Lawton has a cat, maybe I can make the proposition X has a cat. And then you can fill in X with me, with you, with your parents, whatever you want. Okay, this now has a hole that you can fill in, and it's a different statement each time, right? Maybe Lawton has a cat is true if X is equal to Lawton, but maybe if you don't have a cat, maybe you have a dog at your house, then it would be false for you. It depends on what the value of X is. You see the difference there? So a predicate is like almost a proposition. You got to fill in the variables first. And so we write it like this, kind of like a function. We say P of X. Let's define that to be X has a cat. Then you can like fill in a different value for X, like call the predicate, I guess, and call it with me, call it with you, and maybe it's true or false depending. So like P of Lawton. We'll replace the X with me, and then it becomes the proposition Lawton has a cat, which is a true proposition, because I do have a cat. Is true, and that's the idea, okay? A lot of our quantified statements had variables in it, and they can be broken down into the quantified part, and then the thing that they're quantifying over, which is usually going to be a predicate. It's like for all X, P of X is true about it. This would be a statement, right? This is now something you can go and prove true or false. It's a false statement. What does this mean? For all X, P of X is true. Well, if this is what P of X is, it's saying that everybody has a cat. See that? See what that is meaning here? This, taken with our definition of P, it's like for all X, all people, I guess, P of X is true for that particular person, and you give everybody a chance at being X. P of me is true, P of you is true, P of our grandparents is true. That is saying, this statement is saying everybody has a cat. Does that make sense? So that is equivalent to saying everyone has a cat. And likewise, there exists an x such that p of x is true would be like, there is at least one person in the universe that has a cat. Okay? That is what's going on there. Are there any questions about this? What a predicate is, why this means everyone has a cat? All right. This is just weird new syntax. Mathematical syntax, I guess. And so now I'd like to answer this question for you. Like, I would like to prove something. I'd like to say that this thing is true. How can I say it very precisely? How can I convert it to math? All right. So let's just start. This is like the setup. Starting with an English description of an idea. We want to translate that to formal mathematics and then eventually prove it. And one way to prove it is to write a program. All right. So here is my first silly example. Let us talk about this. So here is an idea. There is a prime number that is greater than 50, right? This is a statement. This is a proposition. It's either true or false, right? Either there is a number that's prime greater than 50 or there isn't. Can't be both, can't be neither. So this is actually a proposition. That's good. It can be true or false. And then, okay, let's pretend that there is one. All right, let's call that number that is apparently proving this, let's call it x. All right, what is true about this x? That's what we need to think about. What is true about this x that apparently bears witness to the fact that there is a prime number that's greater than 50? So what's true about this x that proves this? Well, it better be a prime number and it better be greater than 50, right? These two ideas. Whatever this x is, if it's proving this, it must be greater than 50 and it must be prime, all right? What is that but a predicate? You can fill that in with 47, which is maybe a prime number, I can't remember, but it's false for 47, even if it's prime, because the greater than 50 part is not upheld, yeah? That's a predicate. It depends on the value of x, whether it's true or false. And you want to try them all, I guess. And so we can make this look a bit more like math, like what is and, but this little symbol. So let's transform it a little bit more. This looks a bit more like math. And let's pretend that in addition to like x greater than 50 and x is prime, let's write x is prime this way. Prime x is true. Prime of x is true. Because if you write it like this, it's kind of obvious that this is now itself a predicate. It's a smaller predicate inside the bigger one. Does that make sense? Itself a predicate. Because it depends on what you put in for x. If it's prime, it's true. If it's not prime, it's false. Itself a predicate. So like, for example, prime, this is just a mathematical idea, right? Prime of 5 would be a true statement. That's provable. Prime of 6, though, 6 is not a prime number, so that would have been a false use of that predicate. You can't prove that prime of 6 is true. That's an M. Any questions about that? So this is like a big predicate involving, I want to make sure that x is greater than 50 and x is prime, and just checking for primality, proving primality, that itself is a predicate. So it depends on the thing you're checking. If it's a 5, if your x is a 5, then yeah, that's true. But if it's a 6, that's not true. And we want them both sides of this thing to be true. Okay? We still good there. Again, lots of weird looking syntax. But our goal is we want to prove this. There is a prime number that's greater than 50. So we want to find just one good x, right? One good x such that this is true about that x. That will have proven the entire thing. And so with that in mind, if we can find some x, I hope you see where I'm going with that, such that the above idea is true, then the following is true. What does some translate to? That is, of course, there exists. There is some x somewhere such that that is true about the x. So there you go. This is it. There exists an x, here's how you read it. There exists an x such that x is greater than 50 and x is prime. That is what this is asserting. Again, it's something that you would prove. You still have to go and prove it. You have to find a good x and make sure that it all works out. But this is now a statement. This is now something that you can prove. There exists an x. Whereas this one, without the quantifier, it's like, depends on x. It's neither true nor false right now. You got to plug in something for x. And this kind of quantifies over every possible x. Like there is one. There is one x such that x is greater than 50 and it's prime. And so this is a true statement because, of course, there's like maybe, I don't think 51 is prime. That's divisible by 53, right? 53 maybe is prime? I don't know. We'll find out. This is a true statement now. This is now a true proposition. Statement is another word for that. A statement or proposition. Either word works. And what is this inner part but a predicate, something involving a variable, all right? And so every time you use a quantifier, in fact, and I guess I'll just get this all out of the way finally, every time you use a quantifier, you have to quantify over something, some idea, and you have to give that thing a name. So every quantifier is like a way of introducing a brand new variable in your statement, all right? It is how you can go from predicates to propositions. It's always there exists, you put that sign, and then you put a variable. There exists an x, where this is true about x. Or for all y, this is true about y. That's how you quantify over every possible value. You got to give it a name. And so every quantifier creates a new variable, essentially. It's like you're programming in math. Okay? So, again, that was a lot of words, a lot of new stuff. We still good? So I want to prove this now. Now we've gone from English to math. I would like to prove this now. Because it's now just something that's provable. We have to like find an x. So let's do that. Okay, so to prove this, we have to find one good x such that this is true about that x, right? It's greater than 50 and it's prime. So how do we do it? Well, one way to do it is to search. Computers are very fast. We can program a computer to know when a number is prime. We can program a computer to start searching from like 51 and onwards and just stop once it finds a prime number. Hopefully it will find one. If it ever does, we have our x. Does that make sense? So this is an algorithm. You can program this. You can come up with an algorithm to find a prime number that's greater than 50, and the second you do, you will have found one good value for your x. There are of course multiple prime numbers greater than 50, but you just need one, because this there exists is saying there is one good one at least. Could be many. You just have to find one. Okay? So let's think about the strategy. Okay? Let's assume that we have an isPrime function that we can call, and it gives back true if it's a prime number or false if it's not. It's like isPrime. If we call that function in Python on the number 42, it will give back false. But if we call it on like 5, it'll give back true. Right? So what is the idea? How could we search for a prime number that's greater than 50? Well, we're not sure where it is, so it's going to end up being a loop. Let's just be like, okay, start looking at 51. Is that prime? Okay, if it's not, keep going. Look at 52. Is that prime? If that's not, keep going. Look at 53. Is that prime? If it's not, just keep going. If you ever, like if this ever stops and it finds a prime number, right, you will have found something that upholds the predicate that we were looking for. All right, we found our good x. And so that leads into this idea of a program. This is called pseudocode. I don't know if I've talked about that word before in this class. Pseudocode is just like English-looking code. You can translate it to Python. You can translate it to Scratch. It's just some intermediate programming language that we can use to talk about an idea. And so here is the pseudocode for finding the first prime number that's greater than 50. We want to iterate, right? We want to go through all the numbers with maybe a while loop, starting at the number 51, because that's the first number greater than 50, right? The first whole number. We have to make sure that the number we find is greater than 50, because otherwise that whole left side of the and is going to be false, and that's useless. So, like, we're going to use an iteration variable, like I. Call it I. Started at 51. Call isPrime on it. Like, check. Hey, is I prime? Maybe it is, maybe it isn't. If it is, stop. Otherwise, just keep going. Make it 52. Try again. Make it 53. Try again. And just keep on going if you need to. Okay? And so the second this stops, like if I is prime stop, there's a quit function that stops your program in Python. I'll show you that in just a second. But if this program ever stops, we have found a value that's prime and that's greater than 50 by design, and that has proven this statement. Do you see how a program can be a proof to prove this thing true or false? I guess if it loops infinitely, there is no prime number greater than 50, and we wouldn't know if it's true or false because we would have to wait until the universe is over. But if it finds one, it must be true. Okay, so that's going to be our program that we write. It will is correct. Okay. Let's see here. And so I'll open up idle and I'll program this for you. I'm going to write a program that searches for the first prime number greater than 50, and it will prove, once it finds one, that our statement that we were trying to prove really is provable and true. All right, so let's check what lecture number are we? We're lecture 21 today. So I'll make a new file in a folder that you will have later. Let's see, it is on the desktop. This one, 21. So in here, I'll make a new file called prime greater than 50.py. Okay, and so the goal is, let's see if I can make this small because I want to show you the slides. So here's the code. Iterate through all the numbers with the while loop. Call it I to start, and just keep on checking if it's prime. If it is, stop. All right. So like start I at 51. So we want to like. Sorry, I can't show you all this. I guess I can show you all this at once, can I? I'll do it like this. Start I at 51, and is it prime? Like forever. Keep going. Like infinite loop potentially. While true, let's say. While true, I would like to do what? Like I have my I value I'm considering right now. Check if I is prime. If it is, we're done. I'll need an if statement for that. If it is, print it out and stop the program. Otherwise, if it's not prime, we're continuing still. Otherwise, we want to increment I and try again. Come back to the loop on the new value. Otherwise, increment I so that we can check the new value next. And the next iteration of this loop. Okay, so that's the pseudocode, that's the comments. Let's just implement the comments now. So let's assume we have some function called is prime that will give back true if that number that we're checking is in fact prime. So check if I is prime if, right? If is prime of I gives back true, or just like is prime of I gets replaced with true itself. So you can just say it like this. If it is, I'll tab over, I guess. If it is, print it out and stop the program. So we just found our I right now. It happens to be prime. Cool. Let's print it out. And to stop the program in Python, there's a quit function. You can just call it. It will stop this infinite loop, of course, and everything else. That stops the program. Otherwise, if the program didn't stop, we're still here in the loop, and we're going to like come back the next time because this goes on forever until we stop it. So otherwise, increment I so we can check the next value of it, like check 52 next, check 53 next after that. So I equals I plus 1. Okay, so that's going to be our program. And I actually have to show you a secret right now because there is no isPrime function in Python. Or maybe there is in the math library, but it will be a nice sneak peek of what we're going to learn later. I need to make an isPrime function. I'll do that for you right now. So here is, I'm going to secretly make one. You can look away if you'd like. Don't be scared. I'll teach you how to make functions later, but we need this. How do we implement isPrime? How do we check if a number is prime? Here's the algorithm. A number, let's call it n, is prime when it has no factors other than 1 in itself, right? That's what it means to be a prime number when, like, you try to divide 2, 3, all the way to n minus 1. Try to divide all these numbers into n and see if they go in cleanly. If they do, like one of these was a factor, and if it's prime, none of those worked. As long as all those numbers in between 2 and n minus 1 don't divide cleanly. With nothing left over into our original n value that we're checking if it's prime or not. So like 4, for example, is not prime because like you're going to try 2 and 3, try dividing 2 and 3 into 4, and of course 2 works. It goes in cleanly, and so it doesn't work out. But like 5, for example, is a prime number, and you try 2, 3, and 4, try dividing all the numbers that are not 1 in the number into 5, and none of them work out cleanly. It must have been prime. That's one way to check if a number is prime. So let me implement the is prime function for you. I promise I'll teach you how to write your own functions later, but here's the secret. Here's what the syntax looks like ahead of time. You can look away if you're scared. So to make a function, you say def. You say def, I'm about to define this function. It's called is prime. And the thing that it takes is the number that I'm checking if it's prime. I'll call that n. And then the body of this function, the implementation of it, is once I get an n, I want to check if it's prime. I want to try to divide n by 2, 3, all the way to n minus 1. And so I'm going to have to loop. Again, I don't expect you to understand this right now, but come back later, and one day you will. So I want to start trying to divide n by all these numbers, like 2, 3. So let's start an iteration variable. I'll call it j this time. Let's start that at 2. And then I want to keep on looping as long as it's like I want to go from 2 to 3 all the way to n minus 1. So while j is less than or equal to n minus 1, do some stuff with the j, try to divide it, right? And then do j equals j plus 1 to try the next one later. So then it's going to be like 2 first, then 3, then 4, then 5. Yeah, that's the goal. And then every time we have a new number, we want to try to divide n by that number. Try to divide n by this j. And if it goes in cleanly, oh no, we have found a factor and it can't be prime, right? So here's how you check, by the way, in Python. If a number goes cleanly, you use the modulus. Checks for divisibility by a certain number. So like 5 modulus 2 is 1 because you try to divide 5 by 2. It's going to give you the remainder, what's left over, right? So there's 1 left over. It didn't go in cleanly. 4 though, 4 mod 2. Well, you tried to divide 4 by 2. It goes in twice with 0 left over. So that's how you know if your number that you're trying to divide went in cleanly, if you mod by it and get a 0 as the remainder. Okay, so that's what we're going to check. So if n mod j happened to be 0, there was nothing left over when dividing by j, that means it divided cleanly. Oh no, j divided cleanly into n, let's say. So that means j must be a factor. J is a factor of n. Oh no, so that means it can't be prime. Return false. That's how you give back a value from a function. You say return. And so we go along our merry way. If this is a prime number, we're going to try every number, and it's always going to be false here. It's never going to go in cleanly, so we're never going to get to the return false part. Like this loop is going to end. We've tried every number, every possible factor. None of them worked, and we break out of this loop. If we get down here, that must mean that there were no factors. We never said it was false. We never found a counterexample. If we get here, there were no factors. So it must be a prime number after all. We can say that the answer is true. It is prime after all. Okay, so that is how you can check if a number is prime. Please ask me any questions about that after you've studied it. It's a good example, but again, I have not yet taught you how to write your own functions in Python. We just needed this right now. But here is the idea. If I just run this, this is the bulk of it. It's like, remember what we were doing, starting I at 51, checking if I is prime. If it was, print it out and stop. Otherwise, try the next one. Come back here to this loop that's going to repeat forever until we find something prime. And accept. Nice. And so what happened was, it ran. I'll just click cancel here. So it'll close the idle screen if I don't. It ran, it tried 51, it wasn't prime. Oh no. Then it made I52, came back. Was 52 prime? Of course not. And then it made I53. Was 53 prime? And apparently it is. And so it prints it and stops the program. So 53, by the way we wrote this program, right? It is the number. It is the first number, bigger than 50, that is prime. So we've just proven this statement true. Isn't that beautiful? It's all coming together. Are there any questions about what we just did? We proved this statement true using a program. It's totally okay. This is how we can do it. Obviously, you can make a more efficient program. There's a more efficient way to check for primality. You just want to look for one factor, so you don't have to go up to n minus 1. You can go to like the square root of n. Also, you know that no even number is ever going to be prime, so you could add 2 to I each time if you wanted to get there twice as fast. Stuff like that is something that you could do, but this program still works, even if it's a little slow at It could have been faster. Are there any questions about this code down here? This is the main code that I care about you understanding. There's a loop to find prime numbers. All right. Let's see here. So I have another example, another English-looking example that I'd like to have us prove. So let's prove this. Let's prove that for all integers, let's call those integers n, between 0 and 100, I'm claiming that the square root of each of those numbers, right, the square root of n, is always less than or equal to 10. I hope that makes sense. That is a true thing that we could prove, right? It's a true statement because, of course, the square root of 100 is the only time it ever becomes exactly equal to 10. So it's always there or smaller. Like here's the graph of square root. If you go all the way to 100, the square root of 100 is, of course, 10 itself, and everything else is smaller. Like it's everything smaller down here. So this is a true statement, right? But it's English. So step one is to convert this to math. Math like English, okay? And so what does that mean? Here it is. Here's the idea. So for all integers n between 0 and 100, square root of that n is less than or equal to 10. So let's consider that we have some n value. Here's how we pick out the range. If our n value is between 0 and 100, so if it's greater than 0, greater than or equal to 0, and less than or equal to 100, then this must be true about it. That's what I'm asserting. That's what I'm claiming. Do you see how this picks out? It's slightly closer to our mathematical symbols. This idea. Give me an n between 0 and 100. Check that all of them is always less than or equal to 10. So if you have an n and it's between this range, if it's greater than or equal to 0 and it's less than or equal to 100, then its square root should be less than or equal to 10. So that's closer to math. Okay? That's better. And then we have an if-then, which of course we know can be converted to an implication. So convert this to full-blown math, and now it becomes this. So the if-then parts, like here's the if part, here's the then part. You make an arrow between them, right? Implication. So if this is true, then this is true. So that's the same thing all over again. That is our if-then statement in math. It's an implication. So if n is greater than or equal to 0 and n is less than or equal to 100, then this should be true about n. The square root is less than or equal to 10. Okay? And what is this now? What is this looking thing but perfect math? No English left inside of it. And it's a predicate. Do you see how it depends on the value of n? So like if n is 101, all bets are off because you're not fulfilling the if part. We're only considering it when this thing is true about n. But like if n is 99, if n is 98, like then we better make sure like this side is true. See that? If this is true about n, which means it's within the range that we care about, then this should be true about n. That's what we're claiming. And of course it depends on n whether it's true or false. Always. All right? And so finally, we want to get rid of the n. We want to convert the predicate, because it depends on the n. It's not true or false yet. It's neither. To something that we can prove to be true, because we know this should be a true thing. So we have to quantify over the n. For every possible n that we care about, this better be true. Okay? So that is the last thing. All right? Add the quantifier to make a proposition, something that can become proven to be true or false out of this predicate. And so now this is the final statement that we have. For all n, if n is greater than or equal to 0 and n is less than or equal to 100, then the square root of n should be less than or equal to 10. Do you see how we went from English to this very precise mathematical statement? We needed the for all quantifier. For all n's and numbers, if this is true about it, then this better be true about its square root. See that? See how that translates exactly to what we were thinking of? Please yell at me if you have any questions about this stuff. But now, I can say this. So here is how you, I think I just read it perfectly, but if you want to convert this back to English, to very super precise mathematical sounding English, how would you read this? You're saying, for all n, assuming n ranges over numbers, for all n, numbers n, if n is greater than or equal to 0 and n is less than or equal to 100, then the square root of n is less than or equal to 10. Okay? So like if this is true, then this should be true. Make sure that's true for every possible n. Okay? That's the goal. Any questions about any of that, how we got there? Because now I have a question for you. I'll give you my code that I wrote before on the screen. But what I'd like you to do now is, we have discovered this. I would like you to write a program that proves this. Do you see how you might do it? If this is true about n, then this better be true about it too. If n is within this range, then this better be true about n. See, I could check maybe every potential value, assuming n is only whole numbers. Well, I want you to prove that this is true. And to get at square roots, you have to import the math library. So you'd be like math.square root of your number. Math.square root of like 2 or something would give you back the square root of the number. Okay? So using what we were doing here, I don't think you need to see the is prime part. This was the key. The most important stuff was down here. Do you see I can do something similar to prove that this statement is true, that all the numbers between 0 and 100 have a square root less than or equal to 10? Any questions about that? So I'll give you a while to try this. If nothing else, at least write it down in like pseudocode. Like, here's what I would want to do if I could do it in Python. I'll give you a few minutes to think about it. Please ask me any questions that you have while you're working on it. But do you see how you could maybe use a loop again? Check the numbers that are relevant to this proposition. And if you checked them all, then it must have been true, right? I'll show you my answer in a few minutes, but I want to give you some time to try this. couple more minutes. Are there any questions that are coming up as you're trying this? Do you see how you might loop and which values you might loop between? What needs to be checked? All right, so let me show you how I might approach this. It's going to be very similar to the other one. Let's see if you were thinking what I was thinking. So, all right, so we need to prove this. For all n, if n is between this range, assuming it's just a whole number, let's say, then this better be true about it. So here's kind of the setup. Remember that our goal is to prove this idea, right? This English-looking idea that we then converted to math. All numbers n between 0 and 100, the square root of that n, all those n's better be less than or equal to 10. So here's the pseudocode. It's going to be like, all right, well, the numbers that I care about are 0 through 100, so I better just try them all. I better loop through every number n between 0 and 100. Maybe I'll call them I or something. Like I starts out at 0, it can be 1, it can be 2, all the way to 100, because those are the numbers I care about, right? For all numbers between 0 and 100. I need to make sure that this is true about each of them. You see that? That's how you go and prove this. So it's like if I is 0, give me the square root of 0. If I is 1, give me the square root of 1. It's always the square root of I. Give me the square root of 2. Give me the square root of 100. Make sure it's always less than or equal to 10. If it ever isn't, right? If it's ever bigger than 10, for one of these numbers, maybe it's I. I'm using I in my drawing, but I'm saying n in here, sorry. If the square root of the number I'm looking at right now is greater than 10, it was the opposite of what I wanted it to be, then I found a counterexample. Then it's not true that all the numbers between 0 and 100, the square root is less than or equal to 10, because I found one that's bigger than 10. See that? The second you find one of those, then it's immediately false. Everything falls apart. Second I find one that's bigger than 10. You go looking for one that's bigger than 10. If you find one, you messed up. It can't be true. Your statement can't be true. But if the loop stops, notice how I'm de-indenting. If we go through the entire loop, we get finished, we never say false. That means all of them must have worked. They all must have been less than or equal to 10, because this was never true, right? The opposite of greater than is less than or equal to. They must have all been less than or equal to. If so, I mean, I tried all the ones I cared about. They must all be less than or equal to 10. That must prove my statement. You see that? That's the goal. So that leads to a solution that looks very similar to what we did. And let me program it for you. Compare it to what you got. So, I think I can do this again. That works. I'll call this square root proof. So I'm going to import the math library so I can use math.squareroot. And then I want to check all these numbers. I guess, let's see here. I guess I'm calling it n in this thing. So let's just say instead of I, let's call it n. I want to make an n iteration variable that goes between 0 and 100. And I always want to check its square root. All right, so like n starts at 0. While n is less than or equal to 100, like give them all a chance, do something with that, like check it, check the current value, and then make it the next one, n equals n plus 1, right? So the next time it's 1, after that it's 2, all the way to 100, so it's counting up. And what I want to do is make sure it's always, the square root of these numbers is always what I want them to be. If it's not what I want, I have found a counterexample and it can't be true. Right? So if the square root of n happens to be bigger than 10, at that point I have found a counterexample. It can't be true that they're all less than or equal to 10 because I found one bigger. In that case, it's immediately false. I don't have to check anything else. It's like print false. My statement can't be true at this point. Right? Quit the program. Don't have to do anything else. Otherwise, if we didn't say false and stop, this loop will complete. Right? It'll go to completion. It will try every number, and it will make sure they're all less than or equal to 10, because if it was bigger, it would have stopped. If it didn't stop, that means they were all smaller, right? Less than or equal to 10. If we ever get here outside the loop, then it must have been that the statement was true. And so we can say print true. I'll try them all, make sure it all works out, right? So if I run this, here's the full code, right? It's import math at the top. If I run this, it will say true. It will try every number very quickly between 0 and 100, make sure they're all less than or equal to 10, because if it was greater, it would have told me. And we get here. We say it says true, and that proves my statement. That proves that all the numbers between 0 and 100, the square root is less than or equal to 10. That proves this this proposition, right? This proposition is a true statement. We've just shown it. Are there any questions about that? That's the code. We just did it. Is that kind of what you were thinking? Let me show you where there is a counterexample, because if you made a false statement, this should also find the falseness, right? Let's say that we were trying to prove that all the numbers between 0 and 101, the square root was less than or equal to 10. 101 is not going to work, right? And the whole goal is that we try them all. And so we're going to try all the way to 101 this time. And for that one, it's going to notice that the square root is slightly bigger than 10, right? And there's your counterexample. It's like, nope, no thank you, false. On the very last number. So that is how it's going to work. Are there any questions about any of that? So this program can prove your statement's true. There's a way to write a program that proves your statement to be true. We did that for the original one. And of course, programs can also be written that can prove statements false, just like this modified example. Any questions about this? This was a very technical lecture today, I think. Y'all still okay? Our brain's not on fire yet? Good to hear. All right, so yeah, the moral of this story, this is the end of these slides. The moral of this story is that there's a really powerful connection between logic and computer science that you probably won't learn unless you're a computer science major and you get to a 4-year college. But I want to tell you at least a little bit about it, right? This is what these slides are all about. Logic and computer science are better together. If we use both, right? If we use both, we write our very precise logical statements, so logic is very important to start there. If we write those statements, that will help us write a program that can prove them, or write a correct program that will do whatever we want it to do. Like, I would like to write a program that computes if a number is prime. Let's write a logical statement to make sure I understand what it means for a number to be prime. Things like that, okay? So if you combine logic and computer science, good things happen. It's easier to write correct code because you know what it means to be correct. You're proving it to yourself, even in a hand-wavy way. And then also it helps you learn how to spot issues, like learn how to find counterexamples like this last example, right? Which will help you argue why this code looks funny to you. Like, oh, here's the problem, here's the issue, okay? You can kind of spot errors a little bit better because you're thinking logically and you're getting practice with that, okay? So that's kind of the moral of these slides, and that's where I was going with them. I think that is all that I wanted to say about quantifiers and proving things with programs for now. Any questions about anything we talked about today? I believe I have one last thing to tell you, and that is your next programming assignment. So it won't be based off of today's programming lecture. It probably will be based off of last week's programming lecture, when I was making a bunch of random squares of random colors. So I want you to do something similar. This will be due week 14. after spring break and all that. But here's the program I'd like you to write. There's a lot of little requirements, but the title kind of says it all. I'd like you to make a program that uses Turtle and Random, like we've been doing, to do the following. I would like you to first ask the user to enter a number. Don't like hard code. I'm going to make 100 random things. I'm going to make 50 random things. Ask the user to enter a number. How many random shapes do they want drawn? So you get that. Put in a variable somewhere. And then you do the following. Loop this idea n times with a while loop. Like do all this in the body of a while loop. Make it happen n times. Because you're going to draw 100 random shapes. They're either going to be triangles or squares. Like the amount isn't even. It's just going to randomly pick one each time. Okay? So do the following n times, however many the user said what n was. All right? I would like you to pick a random color, right? Set a color variable to like the fill color to a random color. You know how to do that now. I showed you. You can go crazy if you'd like. There are a bunch more colors that Turtle knows how to like draw. So here is the chart of all the fancy colors. Here are all their names. Just put these as strings that Turtle knows how to fill in addition to the ones that I used, if you'd like. So pick a random color, because you're about to draw the next random shape of the N that you're trying to draw. And then I want you to randomly pick whether to draw a square right now or a triangle right now. I want you to flip a coin every time you're about to draw a shape and figure out, okay, am I about to draw a triangle or a square? There will be a lot of if statements in here in the body of this loop. And so the goal is when your program runs, due to this idea, you're going to draw some amount of squares and some amount of triangles, and it's not going to be the same each time. Don't make it like half and half. It should be randomly picking whether it's going to be a square or a triangle each time it's about to draw a new shape. Okay, it's all random. And you can kind of like pick a random number between 1 and 2. If it was 1, make it a square. If it was 2, make it a triangle. Something like that. All right, I can help you with that if you have any trouble. There's a lot of technical details. I want to make sure to tell you all of them. So yeah, the total number of shapes you're going to draw are going to be n, which the user asked for, but they're going to be some amount of squares and triangles. Those will add up to then. Maybe the user asked for 100, for example. All right? And then after that, you're off to the races. Now you know you've picked a random fill color. You figured out if you're about to draw a square or a triangle, and now it's your turn to draw a random square or a random triangle. Right? So pick a size to draw that square/triangle, and then draw whatever one you decided to draw. If it was a square right now or a triangle right now, draw it with that color at that randomly chosen spot of that random size. Okay, like you've been doing, like I've been showing you in class. Okay, so n shapes total, but each time it's like flip a coin. Okay, I'm going to draw a triangle. Flip a coin next time. Okay, I'm going to draw a square now. Maybe you'll draw like 10 triangles in a row. It's random. Okay, so definitely use the code that I wrote and I uploaded from the lecture where I drew a bunch of random squares. Just add the maybe draw a triangle to functionality to that, I think would be the easiest way to go. Are there any questions about this idea? So ask the user for a number, draw that many random squares and triangles. Just n shapes total. Some of them are squares, some of them are triangles, and it's completely random. With fun colors. So this should look very pretty once you do it. But it will take a little bit of work to get there, and that should hopefully be rewarding. Yeah, I think that's all that I wanted to say. So are we good with the description? Just mostly follow this in order. I think it will work. And just yell at me if you have any questions, please. So yeah, just upload a video as usual. Show me it working. Show me it running each time. Make sure it's random. You're not just hard coding things. I want to see you entering different numbers of n and stuff. But yeah, you have plenty of time to do this because there's an extra week, right? And that is spring break, which doesn't count as like a week, really. So that is your programming assignment 7. And did I release it? Yes. So it should be visible to you now. Yeah, the rest of the time is yours to get started on it or to ask any other questions that you have.